So we've been exploring dynamics um, that require thoughtful examination of people over their life courses. And we've seen that even with a sort of modest amount of complexity, two interacting uh, health conditions or behaviors, smoking behavior, and heart disease, and then additional process associated with mortality and fertility or natality. It's actually rather thought-provoking and sometimes counterintuitive behavior that's elicited. We've seen that by tapping the flexibility of agent-based models in terms of reporting different aspects of the state of that model in a way that far exceeds what we can realistically capture epidemiologically in most cases, we can improve our insights into drivers for phenomena in the model. We can note trends, note relationships, associations. And by designing different scenarios, we can probe whence those associations come, primary drivers for trends, reasons that we see certain behavior. We can enable and disable pathways or upregulate them, downregulate them in ways that help us understand where behaviors come from, the degree to which birth rate is contributing, turn off birth rate, turn off initiation, turn it back on and see the differences in ways that are vanishingly rare in public health. And this can sharpen our thinking, better test our model, the plausibility. It can spot gaps in our modeling. The fact that we've had, people able to reproduce even in the oldest ages of their lives led to some bigger differences in the effects multi-generationally scenarios that were counterintuitive. And we saw that using the tools of agent-based modeling were worthy to the task in terms of investigating these and sharpening our thinking. Although this model is a life course model, although it takes into account, an interesting and textured set of interactions, one thing that it lacks is at the very heart of agent-based modeling, namely interactions between agents and agents in the environment. And it is to examine those effects, those sort of effects, we're going to turn next, but also at the same time to build our skills and better sharpen our understanding of the tools of agent-based modeling. So to that end, we're going to be building up a model fittingly from scratch. And this model will allow us to use the toolbox afforded us to probe some of these effects of agent-agent interaction and how they give rise to dynamics at the higher level, both at an aggregate level and associations at an individual level, or across people in the population, I should say, treated as individuals. Okay, we're going to, I'm sorry, I did it without announcing it. We want to do file close or file close all to close out that model. And we will start a new model. Maybe just to layer a yeah, I want to post that model, but let's get going into this. So we're going to start a new model, and to do so, we're going to do file new model. Yeah, and this will be called ABM crowding disparities V1. The model time unit, critically, which is important to capture early, should be a day. So that means 1.0 amount of time, the timeout for timeout transition, or 1 over the value of a rate transition. 1.0 would mean 1 day, not 1 year. Remember, it's not the smallest amount of time that the model moves forward. It's not like a little time step, a time tick. No. This is continuous time, but this is our meter stick or yardstick. Okay, so it's days. And we're going to say finish. Yeah. Oh, did I say AABM? Oh, I said AABM. Okay, well, okay, that's a mistake up with which I will not put. I'm gonna call it ABM. Thank you, Jeff. Low severity, high priority. Okay. So what we're going to do here is rehearse some of the skills we built, but add to them. So firstly, I'd like to go add a new agent type called capital P person. Make sure it's capital. And like before, we're going to lend them a face upon the world. Before, they had a face of platonic beauty, but austerity, namely a little circle. And I asked you to imagine in such circle, 2 eyes and a smile, but we never saw it in its full glory. So here I'd like to add something a little bit more anthropomorphic. So if you can go to the palette, down here towards the bottom, there's a thing called pictures. And I know this will fire some of your imagination. And some of my more mischievous students have employed shapes that I did not designate. And thank you, Jeff. And betrayed the health nature of the model with fighter jets and other shapes. But I'm going to drag down a person here. A person icon. You can choose others, but I'd ask you seriously to use the one because we're going to be setting its properties and so on. And it's important that we have a common reference. So as tempting as that forklift might be, I'd ask you to cease and desist. You can do that in your spare time. Okay. So here's our person. This is going to be called a person icon. Okay. Okay. Next, we're going to add to a person some characteristics. that will be, for the intensive model, pre-specified, specified the initial time, and they'll be constant over time. They'll be invariant. So to do that, we're going to go to our palette. We're going to go to our agent palette, and we're going to drag in a parameter, and we're going to call it income. Okay. We're going to call it, yeah, we'll just call it income. And generally, you give it a name like monthly income or something. This is certainly not daily income. So, okay, I can't resist it. Monthly income. Let's do it while we can. Monthly income. Okay. It turns out we're not going to use it in a way where that's material, but it's the best practice. And I feel bad schooling you in bad practices. Okay, now we're going to go and add to the person a contact rate, okay? And here, this contact rate will allow for people to have a difference in the contact rate that obtains in their particular case. Okay, and this is going to allow for like interventions that affect their contact rate. So specifically if they're masking or something like that, or if they're engaged in distancing. Masking would be more a matter of transmission rate. But if they're engaged in social distancing or something like that. So we're going to have a, oh my gosh, okay, contact rate. Okay, here we go. Both those are double. The monthly income, I'm going to give a default value of 500. $1,000 per month. Sure, $1,000 per month. That's pretty low. I know. And the contact rate, we're going to give a default value of 1.0 per day. Because I declared the model to have a time unit of day, generally I'm going to assume if we don't specify the time unit associated with the contact rate, it'll be per day contacts per day. Okay. And what I'm going to add now is a immunity duration parameter as well. Okay. And I'm doing this partly to teach some lessons about how you can set variable things at a person level, parsimoniously to certain defaults, etc. And this is going to be default 45 days. So it's a short-lived thing, something more like chlamydia, like a bacterial infection. I think gonorrhea also doesn't have a terribly long, again, in that class, doesn't have terribly long durations of immunity. Immunity duration, and finally, duration of infection. Okay. And its default will be 10. These are set at an individual level to allow for variability amongst these things, okay? Okay. Whether we end up fully exercising that in the boot camp will depend on student interests and so on, but they give us that flexibility. Okay. Next, so this is all at an individual level. We've given these characteristics, which can be heterogeneous. Next, we're going to go up to main. We're going to set some parameters for them, okay, for that. Okay. So in main, we're going to have some parameters that will give default values to use at a person level, and reference values that we'll be able to use. So this will be, we'll have a parameter called in main that's called total population. I'm going to call it initial population size. I didn't call it initial before, and I'm feeling guilty because of it. Because it's called population size in that other model, and it could confuse someone because it's initial population size. And I'm not going to repeat it again. Okay. Thank you. Thank you, Jeff. Excellent. Excellent. That's a wonderful way of illustrating. Okay. Initial population size. And there's going to be another one called connection distance threshold. That's something which is going to be shared across the model, hence it's looking at main. Oh, I should have said the connection distance threshold is of distance 100 in abstract units. Again, if you want to interpret the units here, I think each unit here might be, I think it like each of these little squares might be 10 units. But Wade could call this in. Initial population size, its default value would be 1,000, and that will be an integer, not a double. It's a count of things. It's not a continuous quantity like connection distance threshold. Finally, we're almost done with this sort of, time to make the donut stuff. Default contact rate will be a parameter with the default in its name, default contact rate. That will be used by default. If people haven't been intervened upon, it's 1.0 by extension per day. And then finally, default duration of infection by extension, by implication per day. In days, it's 10.0. Not saying what it is in terms of units, so in time units, so it's by implication, it's days. Okay, so this is at a main level. So these are going to inform, like contact rate and duration of infection will inform default values at an individual level, and I'll show you that idiom, that pattern. Okay, so I wanted those set up, and I know it's annoying. And maybe Jeff, you could report these initial population sizes 1,000 by default. Connection distance threshold is 100 by default, 100 spatial units. Default contact rate is 1.0 by default. Default duration of infection is 10.0 by default.
Do you want a default immunity duration as well or not?
Yes, I probably should have that. I don't have it down in my notes, but I thinking ahead, I should probably have that. Default immunity duration. Thank you, Wade. And we'll use that 45. Yeah. Okay. Thank you. Yeah. Okay. Good. Okay, sorry about that, but okay. Okay, now we need to, before there can be people upon the world, there needs to be a population of them. Does anyone remember from the vague people, from the vague recesses of your memory, uh, how we add a population to this model? Does anyone remember how to add it to a model? Well, one way is you can drag in from the agent type whose population you want to create into the model. So from the projects, you go and you grab and you drag. And I think last time I elected not to do this because I want to show how to rename it over here on the right, but then I forgot. So I'm going to go over and rename it population. So what did I do? I clicked here, I dragged in, I dropped it, and I could type population right away if I have presence of mind, but otherwise I go over here and say it. But this is still not a population. Thank you. Yeah, that's awesome. That's an it. That's right. Awesome. Awesome. Thank you. Okay, so this is a population, and it needs to be indicated as such. It's a population of agents. Its initial number of agents will not be fixed, not be a hard-coded value. Instead, it will be given by one of the parameters we created next to it. Which one is it? You tell me.
The initial population size.
Initial population control space. Do it. Yeah. Whatever it is. Up option space or whatever on Mac. Okay. Okay. Okay, now we're going to get into a little bit more texture here. We're going to depart from some of the script thus far. So here we have a population and we have a bunch of parameters. So we're going to start passing through for some of these default values to use by default. They're not intervened upon. So for contact rate, we're going to use default contact rate by default. Okay. Oh my gosh. Oh my gosh. Okay. AnyLogic just exhibited computational distress. Okay. Well, this will be fun to get back. Yeah, that when you edit those properties of particular scenarios, there's some AnyLogic bug that it occasionally bites. It used to be more common, and it caused us distress during the pandemic. But then we ended up it ended up really improving, but now it occasionally is biting me, and it's bitten me twice in this boot camp. Okay, fortunately it auto-saved it, and so we're in pretty good shape. Okay, so for the connection, excuse me, what we should be looking at is the population here. And for the contact rate, so we add initial population size. It's the size of the population. It's a population of agents. Make sure it's a population of agents. Monthly income, you can leave there. We're going to put a formula in a minute. But let's do the obvious ones, or the ones that are straightforward. For contact rate, you're going to put default It's okay. It's the machine is getting very slow. Default contact. Okay, it's getting really slow. Default contact. Okay, default contact rate. Thank you very much. Okay. For immunity duration, default immunity duration. For duration of infection, default duration of infection. So if you want to allow variability between people, you can have an individual level parameters. And then in main, you have some parameters which give maybe means, and you could draw a value from a distribution. We're going to see that in a moment. Or you can pass through default ones and then later update them, say whether according to whether a particular individual is enrolled in a health program of some sort or is intervened upon. Okay, so that's kind of the pattern here. You have these ones at a global level, and you use them to set the ones at an individual level. And we're going to do it most notably for this monthly income. Here, we're going to actually draw from a distribution, and it's going to be a log normal distribution. And really, by all accounts, I should use a parameter. And I'm going to, gosh darn it, I'm going to go do it now. Okay, so it's, so income log mean. And I'm going to do income log standard deviation. Okay. Okay. Income. Well, I'm going to just call it income mean. That's what I'm going to do. Income mean. Mean income. I'll call it income mean. And I'm going to call it income standard deviation. Income mean, I'm going to make it for default. So this is monthly income. I should call it monthly income. Fine. Monthly income mean. Darn it. And I'm actually going to make this 3,000. Okay. I'm sorry. I did these calculations before, and I'm sort of going off script. So give me just a second to see how reasonable this will be as an assumption. Yeah. Okay. 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 Yeah. Well, that's not what I was anticipating. Okay. Fine. I'm sorry, folks. I've set this up to be a nice visual display, and I'm just going to revert here, and I'm just going to hard code it. Forgive me, but I just don't want to screw everything up by futzing with my plan. Okay, so this will draw from a log normal with a mean of 5 and a standard deviation of 2, and I could have computed that from a log mean given or log of some mean, but it's set up to fit within a nice size and to have the contact distance nicely match this. And if I start futzing with it, we might get people not properly connected, and we'll have to tune them before lunch, which I do not want to separate you from your lunch by that. So this is going to be a log normal with a log mean of 5, a log standard deviation of 2, and this is going to be the minimum, which in this case is not binding. For those wondering, you can use at least some versions of AnyLogic. I know there's this little picker here, which is a distribution picker, and you can go and say like log normal, okay, make it mu is 2, make sigma, sorry, mu is 5, sigma is 2, minimum of 0, and get a sense of what it looks like. And basically what you're seeing here is a very long tail. And that's what I'm trying to capture, but at the same time, capture this in a way that's going to be compatible with my assumptions about contact distance. So I don't want to futz with that if I have to. Okay. So we have this set up, and we have all these characteristics set for a person now by default. So that much is good. Now, I think we will post, because this involved rather tedious work here. I am going to post this model. And then, okay, maybe I'll do one more thing. We're going to set their initial location at a specified point. So again, in the population, we're setting characteristics of a given person according to these parameters and so on, some of which are globally specified. Here shows how we can draw for each person their value from a distribution. And we could have done that with these parameters, like draw it from a certain distribution centered there if we wanted to. But now I'm going to the initial location, and I want to make sure the agent is placed in the specified point here. You can see it there, in the specified point. And this point will be specified for the X by their income. I'll be with you in just a second, Sarah. And for the Y, we're going to draw their Y location from a uniform distribution between 0, which will be at the top, to the size of the vertical area we have afforded to us, which is going to be space height. This is asking, hey, what's the height of the space? I'm getting back the space height, and then I'm drawing a uniform distribution between 0 and that space height. Okay, while I'm posting, income, monthly income. And okay, this is important. I have to refer to their monthly income. How can I do that? If I say monthly income, it's going to say, I don't know how to get their income. I don't know what monthly income is. You actually have to refer to the agent at hand. And the agent in this context, it should be clear, like in AnyLogic, there's generally going to be kind of a surrounding agent. The surrounding agent here, however, which you could call through this, is main, because we're in main right now. We're in main, dictating the rules to use for each agent in this population. So how are we going to refer to each agent? Well, you can follow the little thing here, but you use self. See, it says person can be referred to as self. That's the person in the population. So we say my income, self dot monthly income. That's a quite specialized thing. We actually don't use self very much. This is one of the contexts that it occurs. If I want to refer to my for the person being initialized to my characteristic here. The other place you will see it, as Wade will say, quite a lot, is in discrete event simulation. If you're referring to blocks, you can use self to refer to characteristics of a block. But Sarah, you had a question. Hand up.
Yeah, I was just going to ask if there's a reason for the certain parameters being default, but not for monthly income. Is it because
I'm going to be changing? So one of the ways we could go with this model in coming days would be to have interventions that focus on particular individuals and update certain things about them, like their contact rate or their immunity duration, or their infection duration. And those interventions will operate upon a person and change the value of their parameter that then applies. So it's like they're in a certain program which or they're part of a certain intervention cohort which lowers their, engages in social distancing, or works from home or something, in which case their contact rate will go down. So I'm setting them to some default values for now, but the idea is that later, we may dynamically, while the simulation is running, like set some of them to a different value for those specific parameters. That's why those parameters are at an individual level, is so that they can be modified in this case. Monthly income is in a different bucket. Monthly income is captured. It's not going to change, but it's going to be a characteristic which is going to affect their location, and by extension, their proximity to others and their crowding level. So that's why. I don't know if that's helpful, but it's kind of with pre-thought about where we might want to go with this later. It's admittedly a little bit extra mechanism right now that may or may not be needed. But what I did want to show you, what I think is, it's an important pattern, is to be able to see this pattern of like where we set some things at the model level that then let us set some things at the level of main, we set some things which then let us set some things at the individual level. And really, I should have, by all accounts, done that for monthly income. I didn't want to, probably should have used log standard deviation, log mean being 2 and 5 respectively, and as the default, as the mean and log standard deviation and mean standard deviation for income, and then set that. But I didn't want to get bogged down on that. Yeah. Then I thought, well, let's not have them be specified as log, but anyway. Yeah. Okay. So I just distributed that. If anyone wants to get it, I know it's kind of a pain, but we're all set up now. Okay. Now the fun begins. So let's go run this model. Let's go build the model, most importantly. And let's see if it's a happy camper. It's a happy camper. So let's go run it. Okay. So here's our model running. Right now, our model has lots of sound and fury, but it doesn't have much evolution because everything's static. But there's lots of heterogeneity. And one aspect of heterogeneity is setting people's location. The Y location is randomly chosen from you may remember, from a uniform distribution. The Y location is chosen. What determines their X location? What's determining the X location? Their
Income.
Income. So who are these folks way over here on the right? I'll give you a hint. This is increasing X. So who are these folks over here on the right? Those are
Rich people.
Yeah, those are rich people. And the folks here on the left, who are they? Poor people. And you'll notice that it's not uniform. It's a log normal distribution. So there's a long tail. And these folks, a lot more people per unit area than the folks on the right. Okay. And that's going to make all the difference in the patterns that are coming out of it. Okay. So we have income-based heterogeneity in terms of their location. Yes, Roselle.
So, Professor, the way we distributed the monthly income using log normals in the initial population.
I'm sorry, I didn't catch that. Say that again.
We distributed the monthly income using log normal distribution, right, for the agent.
Sorry. Yes, we distributed their monthly income at an individual level by drawing from a log normal distribution. Yep. Mm-hmm.
And when over the time, the distribution will be the same kind of thing for the agent, or it will change over the time?
No,
when the new people will come.
This is a model of infection spread, and we assume that the income is not evolving over the time frame of the model.
Okay.
We're also not simulating aging in this model. Models have boundaries, and if you're simulating the spread of a outbreak within, a period of a few months, you commonly don't take into account people being born, for example. And you may not take into account people's aging at all. I mean, generally, you won't take into account people's aging. Whether you take into account mortality depends on the characteristics of that infection, because the period of time is short enough that you don't have to consider certain demographic effects. They don't materially impact the outcomes. And this is something we have to do very carefully when we build the model, is set the boundaries. And if we had to do a full demographic model for every investigation, it would have huge costs in terms of the learnings, because we would end up doing a lot of work for little purpose and get little bang for the buck. So we have to be judicious about where we put our time, just like not every model has a full characterization of people's educational journey, or of the specific barriers associated with their geographic location, because those barriers will be different and the relevance of education will be very different by context. So here, income is treated as, for the sake of this model, like aging, as more or less constant. Okay, so here we are going to next impose some network structure on this model. Okay. And this network structure is going to be spatially mediated. In other words, two people A and B are going to be connected if and only if, in this case, they lie within a certain distance of one another. And the distance is given here as this connection distance threshold. Okay. So here, we're going to go to that population, and we're going to go down to an area. We're going to go to Maine, not that population. You do things at a population level, but we're going to be going to Maine. We'll go down to space and network in Maine. Okay, this area which we have not yet used. Okay, space and network. And what we're going to do there is configure a network type that we're going to employ. So here, we will be making use of one of the predefined network types. You can set your own. You can build it from empirical data if you have that. bearing in mind that you're going to need empirical data on the underlying network, not just, generally not just the subparts you happen to have observed. So you have to be a bit cautious about assuming that the observed network is always the same as the unobserved one. For example, in areas like contact tracing patterns, you may have data from contact tracing, but what you often won't pick up is data on who else contacts were contact with it. So it's not necessarily a perfect reflection of the network structure of the population. In fact, it rarely is. Okay, so in the space and network area, you go to network type, and this is a distance-based connection with a connection range. Again, this is the range, the threshold that will determine if two people are connected. A and B will be connected if and only if they lie within this distance and in continuous space. So this distance is connection distance threshold. Okay, so that's step one for adding the network. We're going to connect them we're going to impose a distance-based network, and they're going to be connected if they lie within this distance. The next step is to go to a person and configure what that network looks like for their default connections. In general, in any logic, a person can have many sorts of connections. For example, they can have family connections. They could have network connections that are more technology mediated, like friends on a certain set-controlled network program. They could have many such connections. They could have collegial networks. They could have sexual networks. They could have many types of connections. And in general, you're going to want to put those in different types of connections. But there's a built-in one, which is provided by default. If you only have one type to focus on for a model, you can use this. And it makes it especially easy by default to refer to this. And that's what we'll do. So we went to person. Notice I'm in person. I'm not in main. I'm in person. This is extremely important. So I'm currently focused on person. In general, as I said the first day, you want to be clear. What's your frame here? Your frame is person. You are setting the appearances of each person's connections. Okay? You don't want to get confused because main also has connections. As an agent, it has connection. You don't want to be futzing with those. You want person's connection. You may ask, why does main need? Well, look, people in general can be inside neighborhoods, for example, or inside schools, and neighborhoods might have connections with nearby neighborhoods. Or maybe they're in a city, and cities have connections with each other that are spatially mediated. Here we're in person, and we want to go to the characteristics of the person. Okay, the connections of a person can connect to others. We're going to set it so that they're connected to other persons, okay? And that will simplify some of our life. The fact that we know that their connections are all persons as well. You may ask, well, who else could it be? Well, in general, our models may have many types of agents. We have models Jeff has worked on with service dog agents and people agents, for example, or other other models where we have, population member persons, and then we have types of clinicians, for example, or these could include social workers or primary care physicians or addictions medicine specialists. There might be models where you have people and community-based organizations as other types of agents. So in general, you'll have more than one agent, and you want to be clear, like a given network, whom does it connect? Is it just any old agent, or is it connected specifically to a subtype? If so, mention that subtype, and any logical belief will give you less grief. You'll have to do less work in certain contexts. So make clear it's connecting to persons. And in the communication area, we won't do anything. This is a good area if you want to route the message in the future to certain state charts and not others. You can set that there, and sometimes you want to check that. The most important thing I want to communicate to you here is we want to draw a line between connecting agents, or between agents that are connected. And we could choose whether to draw it behind them or on top of them. I'm going to choose it to draw it behind them. Okay. And now I'm going to save it. For those wondering, a network can be static or dynamic. You can change its connections, or you can set them at first. Here, we're going to set them at first, and they're going to remain static after that. Okay, so I built this model. I'm going to call this model version 2. I should have done that earlier, but better late than never. And now we're going to build it again. I mean, I built it before. It's a happy camper. I'm going to run it. And what we're going to see is, well, people connected up via network. Now, these networks exhibit, so networks capture topology. They capture who is connected with whom. I would note that this network exhibits a non-uniform connectedness. The degree centrality, to use the words of, the terminology of social network analysis, of a person out here to the right, the number of neighbors that they have in the network per person out here is quite different than in this area among these folks. Who are these folks? Can anyone remind us? We said it earlier. Sarah said it earlier. Who are these folks? They're the people with lower what? Begins with
Lower
Income.
lower income. These are folks with higher income. The people with lower income have more crowded conditions. People with higher income have less crowded conditions, right? And it's mediated by income. More than that, there's a bunch of people out here to the right that are in sort of islands on their own, that are not even connected. They're not even reachable by these ones on the left. They're in their gated compounds. Okay. The plot thickens. Okay. So I distributed that model. Or did I do it at the latest change? Maybe I will upgrade it. Forgive me, I don't remember, but here's version 2, my current version. If anyone wants to grab that, they are welcome to do so. This has the network in it, connectivity, etc. Okay. By the way, if you don't configure that individual's connections to be connected with a visual line, the network will be there. You just won't see it. And it can be hard to interpret things sometimes if you don't see that network. So making that network visible is a good thing to do to get insight as to the underlying dynamics when networks are important mediators for processes in the model, as they are here. But now we need to get to those underlying processes. Okay. So to do that, we're going to build on skills you've already built up with building state charts. So this is familiar stomping grounds. We're going to drag in a state chart entry point, and this is going to be called an infection state chart. Make sure you're dragging in the entry point, not the initial state point, the entry point. This one up here. Somehow my chat window disappeared. There it is. Okay. Okay. Next, we're going to put in a state here called susceptible. Another state called infective. And another state called recovered. You may note the shift here. I'm talking about a context of contagion, and I'm talking about communicable disease context, so contagion of pathogen. But I want to emphasize, like that model we were working on till this very morning, like with smoking. There are versions of it, and I'm glad to lead you through an exercise if it's an interest, where we have social effects in smoking. And so we use networks just like we've created in that context to shape people's smoking behavior. So my likelihood of initiating is influenced by the prevalence of smokers in my social network, my particular social network, my neighbors in the network. My likelihood of being able to avoid relapsing might be set by that too. If so many of a large fraction of my closest friends are smokers, maybe that will make it hard for me to quit or to avoid relapse. So please don't think like this is now we're switching into AnyLogic's communicable disease mode. No. Like networks are great with behavioral factors related to chronic disease or behavioral epidemiology. And I'm glad to show mixes and matches of them. It's just I want to show a certain repertoire here with networks. And I do want to show you what communicable disease example, because some people's interest may be in that area. There are some also distinctions here about like how the network plays a role here that are that will differ by areas. And sorry, I have a okay. 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 Okay, sorry about this. Thank you. Okay. So appreciate that. So grateful. Okay, so there are differences in how networks play a role, the function of them. For example, here they'll be in the context of transmitting sort of like discrete occurrences of exposures, like I expose you to pathogen. In other contexts, it might be more cumulative impact. Thanks, Joe. Yes. I'm very, very fortunate to have this here. In other contexts, there are cumulative effects of social norms or impacts of the people that surround me and my attitudes, knowledge, behavior, beliefs, and whether we characterize it as kind of a gradual impact on my hazard rates, like likelihood of uptaking smoking is affected by how many people around me are smokers themselves, or whether we have it as more of like a discrete thing, like, oh, I got infected by a bloodborne infection, or I was transmitted a conspiracy theory about vaccines, and now I have this, bizarro belief about vaccines. like whether we treat that as like a discrete effect or more of a continuous effect, we have the option of doing both. Like we could, or of choosing between those. And if there's participant interest, let me know, and I can feature, situations where networks play a different role in mediating effects. There are also cases where networks are dynamic. We choose our friends, and our friends, we elect our friends, and then our friends shape us. Winston Churchill once said about buildings: we build our buildings, and our buildings shape us. And that's true. And it's the same thing with our social networks. So networks have great significance and great versatility, both more generally in health and agent-based modeling, and in any logic in particular. And I'm always glad to show this, and evolving networks, direct contact infections. Yeah, I'm glad to show direct contact infections. If you're interested, like people transmitting it from nose to nose contact for cows, or for from bloodborne infections by needle sharing or something like that. They could conjure up something. Okay. And there's some reference models that I could refer to. Okay. So here we have a little state chart. We're going to put in transmission connection. We're going to put in a recovery transition. And then, and this is absolutely, well, I think we'll make this point more demonstrative in a minute. So we're going to have, this one will be called transmission. No, we could call it pathogen transmission. We could call it infection transmission, etc.
Transmission is good.
What's that?
Transmission sounds good.
Okay. This is going to be mediated by something new upon the world: a message. The occurrence of a message. Okay. And we can elaborate that later in terms of how it has effect and so on. But for now, we'll start simple. And then there'll be a recovery transition that will be given by a rate. And this rate will be given by, you may remember, it's a general fact about mathematical statistics and the stochastic processes. If you have, I'm not leaving that as 1.0. If you have an average time that you spend infected of duration of infection, the rate of leaving that will realize that as the mean time, an exponential distribution that's applied for a certain chance per day that's fixed of leaving, conditional being in that, is 1.0 divided by that. And I've mentioned this at several times, right? If you have a 10 days on average you spend infective, then your chance per leaving per day is 0.1, 1 over that. And it kind of makes sense if you want to think about it. It's like, okay, of the people in that state, if we think about all the people in the population of that state, this is depicting a particular person. If you think of all the people in the population of the state, about 10% of them turn over at each day, right? For it to be 10 days on average from there. If the duration of infection was on average 2, about half of them will leave each day. Turn over about half each day. So it's 1 over it. Okay. Hope that makes sense. And so that's good, but I'm actually going to, I'm gonna do something a little bit different. Look at my notes. I'm gonna set this to be a timeout. So there you leave after that amount of time. Now, for those wondering, I could draw it from a distribution as mean as this, but it's, it's a truncated normal or some a uniform between half of this and twice it or whatever. I'm just going to make it leave after this amount of time. Okay. Now, mind you, people can have different values for this, and so it'll vary as a characteristic of the person. Okay. Thank you, Joe. Okay. Now, we are going to now have to dictate this. And later we'll have a waning of immunity, but we're not going to do it yet because I want to make a point. Structure determines behavior. Okay. So we're going to introduce something you haven't seen before. And then we're going to do something we have seen before and should be very familiar. So I'm going to introduce a way of distinguishing a set of nominal names and names for nominal quantities. When I say nominal, sometimes these are called categorical quantities in a statistics context. And what I mean is they're alternatives, specific nominal alternative. They're not ordinal. Not one is bigger than the other. It's not continuous. It's not a count. It's just a set of possibilities. And this possibility will be called message types. Okay. So I'm going to go over here to the model, over here in the projects window. And I'm going to add in an option list to list types of possibilities. And this is going to be called message type. And I'm going to have an exposed message. In general, though, I actually want to teach you how to. Oh, where'd that go? That's weird. Okay. I thought I entered that. That's weird. Okay. So there's a type called exposed. Boom. There we go. Message type. And this is a set of possibilities. Later, we may have others like force infection and other things like that. Like, you are vaccinated. Here, we're just going to have exposed. This is really handy if you want to distinguish between men and women. Someone self-identifies and non-binary, or you want to have biological sex male, sex female. You can put them in here, and then you can refer to them, and you can set parameters that says it's their biological sex at birth, and you can use that as the characteristic to keep track of these nominal quantities. Okay. So this is called message type. Right now, it'll be a single thing. Later, we could put in vaccination or what have you. Okay, so that's one thing. I added that to the model as a whole. And now, for this transition, I'm going to have it be set on a certain message type. It's triggered by a message of a certain on a particular message, and the message is exposed. If I'm sent a message that says exposed, I'll say, yes, ma'am, and I will get infected. I'll make this transition. And this could let me have another one and another state chart for vaccination, or, you know, some other thing here, another transition, which would be contingent on for vaccination to a vaccine state. So I could have like an exposed message takes me this way, a vaccinate message takes me that way. Just think ahead. Okay. So that may be new, but we want to complete the thought. Just about. Okay. So we're going to go and we're going to put a transition from infective to itself. You may remember this. We did something like this the very morning for bursts occurring when someone's in their reproductive years. It was sort of firing with a certain rate, birth rate for reproductive years. Here it's the same idea. So this is going to be called a contact. That's not too bad. Contact. And it's going to be a rate transition with a rate given by what? What do you think might set its rate? What thing do we have sitting around that might set its rate? Thank you, Wade. Awesome. Yeah, the point is by naming it with an option list, we avoid typos because it can be potentially very frustrating if you just put a string and sometimes you capitalize it and sometimes not, and you get totally different behavior and it's inconsistent and the model doesn't work and you can't present it, and or there's a bug in the paper and you have to go modify the results or whatever. Anyway, so I'm going to use my contact rate. Person's contact rate as the rate at which this fires. And this, you may remember, for this one, the timeout was given by duration of infection. This one is triggered by a receiving an exposed message. Again, if I said exposed, it's very subject to mistyping. If I were to send one like that, it wouldn't recognize it as this. If I forget to put in the exclamation point, it won't recognize it. And in general, it'll take more work to recognize it. Or it could. And so, in general, it's not robust. Here, you're guarding against errors. You're guarding against mistakes. You're heading off mistakes. You're heading off grief. Take it from an open main. Okay. So we're getting close. We're going to have this thing working in its basic form before lunch. Okay. So let's I know for the East Coast folks, lunch is come and gone. If you're okay. So folks, let's just complete the thoughts here and then we'll break. Okay. So the next step is something you're very familiar with. We want to set a color to make them change color based on their infection status. How could I do that? How could I have this little icon change color depending on their infection status? What could I do? Where have you seen this pattern before, this idiom?
We need to add a variable first.
Yeah, we add a variable of type what?
Color of type.
Color. Yeah, type color. So this is their infection. I'm going to call it infection color. And I'm going to put a U, but you don't have to do that. If you don't want to. No pun intended. Okay, so infection color is of type color without a U, because it's set by an American company. Oracle. And the initial value here will be black. You may remember this thing before. Same basic shtick. A little bit more to hitch it up to this anthropomorphic image. We'll see. But all right. Okay. Next, we're going to have to, how do we make that variable change based on their status? Where do we go? Where do we go? Each state has got to change it. Remember this? I think you've done this pattern several times before, right? So what do I type?
Isn't instead something?
Sorry?
Is isn't dot instead?
No, no, no. I want to set this variable to have different colors. So what do I do? I need to set the variable to a particular color. So how do I do that here? Anyone? Infection color equals red or green or whatever I want it to be. Here, I'll say red. Sorry, green for this. Green for susceptible, red for infective, gray. Is it with Y or E? Is it Y? Yes, gray. Okay, gray. Okay, so I'm setting it for each of these. Here, green. Here, red. Here, gray. Good. But is this going to actually, so far, if I just ran this, would it change their color? Would it, in fact, operationalize their color will change? What's missing? We're not changing this icon's color, in fact. We're saying this is infection color, but we're not, in fact, enacting it as like a change in this visual representation. To do that, we have to complete the thought. We have to go somehow frob this icon. Now, you can do this visually, particularly if you zoom in, but I find it easier to go over here under person and presentation and under level and person icon. There's a shape body. Okay. And I know that may sound like a an ad for a spa or something, or an exercise place, but it's it's a name of this kind of the shape that forms the body of this anthropomorphic icon. We're going to go down to appearance, and we're going to set their fill color. Excuse me. Remember, we have to do this to set it to that. We have to have this so it dynamically calculates it, and we're going to set it to infection color, just like that. And I think I'll also use it for their line color, just so that we don't lose out on. Okay. Okay. Okay, so we're almost done. But there's an important thing that if we run this model now, we actually won't see any sort of infection spread. Everyone in this model is in what state based on their color? It's in what? What state are they in?
Susceptible.
They're susceptible. So to kick off an infection, just like to kick off a fire, we need a spark. To kick off a spread of infection, we need a patient zero, an initially infected person. And you've seen this before. So I'm going to do it this way. We could send a message to a certain number of people, but I'm going to do it this way. I'm going to go and we're going to have most people start susceptible. That's going to be the default. This is going to be initially susceptible. And the rest are going to start infective. Hey, oh, come on. Come on. And this is going to be conditional. This is going to be initially infective. And I'm going to add to main a parameter. I probably should have done this earlier. I apologize. But it's going to be fraction. Maybe we'll call it, with a nod to terminology in the health science, proportion initially infective. And its default value be 0.05. Maybe make it less than that, 0.02. Proportion initially infective. And then in person, so what did I do? I added a parameter to main called proportion initially infective. And then in person, they will go to the infective state if they flip a coin and they're one of these 2% on average. there's going to be random true, which is basically flip a coin with this probability of being head. So if this is true, it'll be true with that probability given by this, like 0.02, 2%. Then we'll go to the infective state. Otherwise, we'll go to the susceptible state. Okay. And that's it. In other words, they're going to come in, a given person, at the start of the model. No people are going to come into this model. No people are going to leave it. It's just going to be a cohort. It's just going to be a fixed population. They're going to come in, and their eyes are going to go down to susceptible by default. But if they flip a coin with a certain small chance, they'll start infected. And the small chance is given by this proportion initially effective, 0.02. So 2%. Yeah. Okay, make sure it builds. I'll distribute this to everyone. Oh, proportion. Oh, of course.
Should be main dot, right? Main dot.
So I meant, no, I meant main dot. Main dot. Main dot. It needs a main because it lives in main. This parameter lives in main. So for in person, we have to refer to it up in main. It's not that it's going to vary per person. No. It's just one parameter for the whole population. It's a parameter. It's a parameter about the whole population level. The proportion of the whole population that's initially infected when we want to refer to that. Okay. There we go. Now let's run this thing. Here we go. Okay, who are the reds? Anyone? Okay, well, looks like it's interesting. Looks like oh, of course, we haven't sent the spark. They started red, but we need them to actually, we didn't fill in an action for the contact rate. Okay, so this is the final thought here. And then we'll break for lunch. So in the action, we want send to random connected. That means they're going to send it to one of their neighbors in the network. And what are we going to send them? What message are we going to send them? What message type are we going to send them? Guess what? The only type there is, and that is what? Yeah, and it'll auto-complete it. Sorry. I was mistyping that it's case. If I put it in quotes, it wouldn't have done it. But here it knows that message, exposed, because we declared it among our message types. So it knows how to fill it out. It knows how to auto-complete it. It knows how to send it properly. If I'd done a quote, it wouldn't have matched in case, and we would have been delayed in our lunch. So let's go run this thing. So periodically, a person who's infected will be sending that message. And here we go. Here's the 2% that are initially infected. And it's spreading. It's spreading across our network. There we go. It's like a lot of people have gotten infected and now they recover. And now it dies out. Okay. So it's died out. Okay. Good. And we could add one thing in here of loss of immunity, but I think I'd rather have you go to your go to your lunch, and we can do that afterwards. Right now, the infection spreads, and then it peters out because everyone has been infected. But after lunch, we're going to add a loss of immunity. And if you feel bold, you could do it over lunch or before we reconvene. Ooh. What you have to do is rather simple. You need to put a transition from recovered to susceptible, a rate transition with rate given by 1 over the immunity duration. So if you want to try a little challenge, just do that and see the results. Otherwise, we'll do it together after lunch. Thank you. We'll see you in an hour's time. 12:30. Well, that's right, in an hour's time, whatever it is, your time zone. Take care there.